Hello, good afternoon, good morning, good day to whoever you are, wherever you are around the world, and welcome to Haystack Live. This is our meetup concerned with all topics around search and relevance. We've got a fantastic speaker today, someone I've known for a long time, working in the area of search and relevance, Alessandro Benedetti, who's going to be talking about testing, learning to rank with interleaving on Solr. Just before we get started, a few house rules. If you keep your microphone muted, that would be really helpful. If there's any background noise, I may have to mute you. If you have questions for Alessandro, you can write them in the Zoom chat. And then at the end of his talk, I'll be asking them on your behalf. I'll make an attempt to get all of your questions answered, but I'll make sure those who ask lots of questions only get their first one asked first, and then they can take a turn with everybody else. We're recording the meetup, which will be on our YouTube later. Let me just see if I've actually got that. Yes, I have even started the recording. How fantastic. A few other things just to make you aware of. We run these meetups every few weeks. They do very much depend on getting excellent speakers like Alessandro. So if you have a talk you can give on search and relevance, please go to the Haystack website. You can see the URL there at the bottom of the screen and register your interest. While you're there, of course, you could buy tickets for Haystack US in Charlottesville, which is coming up at the end of April. This is our first visit back to Charlottesville in a while. We're expecting a fantastic conference. We'll have 2 tracks of talks over 2 days, social events, networking opportunities, and a great chance to meet other folks in the search and relevance community. So do check that out. We'll be publishing the talk schedule hopefully next week. But of course, the event's going to be so marvelous, you should buy your ticket anyway. So do check it out. There is an early bird discount. And I think without further ado, I should now hand over to Alessandro. So if I just stop my screen share there. Alessandro, would you like to, well, firstly, who is Alessandro Benedetti? A mainstay of the Lucene Solr meetup, where I spent many great times chatting to him about search and relevance. Based in London, founder and director of CAs or Cs. I can never remember how to pronounce it, Alessandro. I'm very sorry.
Yes. Cs is fine.
Cs is fine. And of course, the mainstay of the Solr project. And I believe you were recently made a committer on Solr. Is that correct?
Lucene and Solr committer and PMC member.
Fantastic. Well, without further ado, I shall hand over to Alessandro now, who'll give us his talk. And I do hope you enjoy it. And we shall see you at the end of questions.
Thank you. Thank you, Charlie, for the kind introduction, and welcome everybody. Today, I'm going to talk about online testing, learning to rank models with the Apache Solr interleaving component. So we had the introduction already, so very few words about myself. I'm an R&D software engineer and director of my company. I have a master in computer science, and I'm a program committee member for the CIR, SIG-IR, and the SIRES conferences. They are academic conferences, but they have an industrial track, so check them because they are quite interesting. And Lucene and Solr PMC member and committer. I've been working with Lucene and Solr for many years and trying to be as active as possible in the community. I work with Elasticsearch as well, and I'm very passionate about integrating machine learning, natural language processing, and semantic technologies with search to improve the search experience. Beach volleyball and snowboarding, something I don't do in London because there's not much snow nor sand, but I do them back in Italy when I go for summer or winter. So what it is, so we are information retrieval experts. We work with open source technologies such as Apache Solr, Lucene, and Elasticsearch, Vespa, OpenSearch, and we are actively researching in the field of neural search, natural language processing, learning to rank, document similarity, such as the more like this functionality in Apache Lucene. And we try to contribute as much as possible to the community through the mailing list, contribution to code, to Lucene and Solr. We contributed the Reddit Ranking Evaluator, which is an open source library for search quality evaluation, and many other things. So, and among the others, the learning to rank interleaving component, which we are going to explore today. So a quick summary of the agenda for today. We're going to introduce learning to rank as a technology, just to give you an idea of what we are talking about when we are going to then describe interleaving to evaluate learning to rank models. Effectively, interleaving can be used to evaluate any ranking model, but it is integrated currently in Apache Solr, mostly in the learning to rank component. We're going to describe why online testing in general is good for your business or for your enterprise, and why interleaving is acquiring a lot of popularity and it's becoming more and more important over the years. Then I'm going to talk about the Apache Solr implementation I contributed, and that's available from Solr 8.8, and also some demo requests and some results coming from Solr to show you how you can use it. So let's start from learning to rank. So learning to rank is an application of machine learning that aims to learn from the user experience, so user interactions, implicit or explicit feedback, to rank documents. And for documents, we mean any kind of document, so any entity you could store in a search engine. Can be like effectively a document, a legal document, a news article, an e-commerce product, and on and on and on. So at the beginning of learning to rank, it was just applying standard classification or regression algorithms already present in the machine learning community to the ranking problem. But with the time passing, researchers realized that the ranking problem is a specific problem on its own. So it's not just a matter of predicting a score, predicting a relevance score, but is actually a different problem because you want to sort a set of search results. So you want to actually work on a list. So we are not going to talk that much about learning to rank. Probably you are familiar with this technology and you can find plenty of documentation online. But just to let you know that over the last few years, many different techniques have been studied, researched, and published on learning to rank. So just a quick glance to what is not. So learning to rank is not something that learns by its own. So it's not, there are like online machine learning technologies that can be used for learning to rank to continuously learn, but it's not something that can do that autonomously. So you need to be very careful that it's not something you can just install, plug it in, and use it in your search engine. It takes patience, time for sure, and multiple iterations and experiments. And it's not easy to explain. Machine learning models in general are not easy to explain, and learning to rank models make no exception. So we are talking about potentially complex tree forest-based models, so like decision trees-based models, neural network-based models. So it's not easy to understand a search result coming from a learning to rank algorithm. So why is that? Why the score is like that? Of course, researchers and practitioners are working toward that direction. So we are seeing progress. So the application of learning to rank happens at ranking time. So you have some documents in your index. You retrieve a top K list of documents, applying some lexical ranking algorithms such as retrieval and ranking algorithms such as BM25, for example. And then you can spend more time on the more expensive calculation necessary for learning to rank models scoring with only working on the top K, so the top 1000, for example. And the ranking model needs to be trained. So you need to train first your learning to rank model, and then you can use your learning to rank model online in real time to re-rank basically your top results. We briefly talk about training data. when you train learning-to-rank models, you can use explicit user interactions, judgments, so query document pairs with rating, relevance rating, or implicit user interactions, so user interacting with the search results, clicking, adding to cart, downloading results, and on and on and on. So you can estimate the query document relevance based on those implicit interactions. So what's online testing then? So online testing means you deploy online your learning-to-rank model, and you want to understand how it behaves, if it's good for your search problem, and how it compares with another model, for example, or your original model. So even not your learned model, maybe just a lexical DM25 ranking algorithm. Now, most of you will be familiar with offline search quality evaluation and offline testing. That's something, of course, encouraged, and before you go live, it's absolutely very important to first monitor offline the behavior of your search engine. And you can do that, for example, building a test set containing query document pairs and checking the NDCG, for example, some metric of your interest. We are not going to talk that much about metrics, but you can calculate a relevant score for your queries. So to understand if your search engine, if your learning-to-rank model is behaving fine on your test set. But the test set is something artificially made, can be built, for example, collecting user interactions, as I said, estimating relevance, the same data you use for training. Now, this is, of course, really important, but it's different from your real users, so the end users. Now, building an incorrect test set, or for example, a test set that is too small, can give you a false idea of how your learning-to-rank model you just developed and you want to deploy to your production is behaving. So you may be fooled that it's performing really well offline, but maybe it's not really the best solution for your search problem. So you shouldn't go live blindly, just pushing it online, leave it there for your users to use it. And especially if you have already another model in place. So you shouldn't rely only on the offline comparison, because as I said, it could be flawed. There could be many reasons why your test set is not actually valid to really test your newly developed learning-to-rank model. You could have various queries in your test set, but in each query group, potentially you could have just one sample. So when you just rank just one sample, whatever is the model, you're going to get just that document. So that's not going to help. It's going to boost the score of your model without really any reason. And potentially you could have like a test set that assign multiple samples to each query, but all of them with the same relevance label. So also in that case, you would get the maximum metric calculation, whatever is the ranking, because if all the documents for a given query have the same relevance label, whatever the order, the NDCG, for example, won't change. NDCG, for the people that are not familiar, is a metric to calculate how relevant are search results for a given query, and takes into account the graded relevance label of each document, query document pair, and the position of the document in the search results. So if you have just one relevant label, even if you have 100 results, whatever is the order, NDCG won't change, or any kind of important evaluation metric. If the relevance label is the same, won't really matter. And given the fact it's artificially built, the interaction you are considering may not be exactly what you want. So they could not be aligned with the user intention, for example, the real user behavior. And you want to know if the live results are reflecting the benefits you're seeing offline. Now, the advantages of going with online testing, and we're going to see quickly a couple of types, briefly the A/B testing, and then the focus of the talk, which is the interleaving, are the reliability of the results, because we directly observe the end user behavior. So that's what we want to optimize. Of course, learning to rank models may even optimize business requirements, that's fine, but you want to make sure that your users are interacting with the model in the way you are expecting. And the fact that you are reducing the indirection is the interpretation of the results. So you may realize that your model, for example, behaves poorly for a certain group of users, a certain group of user requirements, effectively. And monitoring online can give you also the possibility of observing unexpected behavior and then model that behavior, so improve your model. So what are the different types of online testing then? I will just cite a couple of them. One of the most popular, probably the most popular nowadays live, is the A/B testing. So that happens for many things. So it can happen on a website, on a search engine, also for ranking models. So you could have like a control model and you direct half of your population to the control model and half of your population to a variation model. So you will literally split your users in different groups, and one of the group will see one ranking model, another group will see another ranking model, and then you can compare some online metrics, such as the click-through rate, the add-to-cart rate, the sales happening in each of those two groups, and on and on and on. So this was probably the first online testing approach that came to the industry, is still widely used, but interleaving can improve certain aspects of that. So first of all, what is interleaving as a concept? So you have two models and you are presenting to your users just one search result list. And this search result list is going to interleave results from the ranked list of the first model and the ranked list of the second model. So we are going to use both the result sets to build just one result set to be shown to the final users. There are different ways of building these interleaved ranked list. We're going to see a couple with a focus on the Team-Draft Interleaving, which is implemented in Apache Solr. So the users see just one ranked list. This ranked list can change depending on random factors, potentially, depending on the interleaving algorithm. But the important thing is that there are no strict distinctions. So it's not that one part of the population sees one ranking model and another part of the population sees another, but we see the results mixed up. And the users will interact with each of the results, and we're going to keep track of the results the users interact, because we want to understand, for example, if the users are, in average, clicking more on the results coming from the model A, or potentially on the results coming from the model B. So this is how you produce the user interface, so how you actually return a ranked list to the users. But how do you estimate a winner? So how you can calculate, out of a period of time when an interleaving experiment is running, which model among the two you're interleaving, for example. Potentially you could interleave more, but Apache Solr supports, and most of the interleaving algorithms anyway were optimized to support two ranking models. So how can you discover who's the winner? So the delta AB score is a mathematical formula quite simple, to be honest, to calculate the winner of an interleaving session. And it's just counting, to make it simple, the number of queries that are a win for the ranking model A, and counting the number of queries that are a winner for the model B. Then if you have a greater number of wins for the model A, so you basically get many more clicks on items that were belonging to the model A, you're going to get that model as a winner. And if you got more clicks on elements from the model B, you get a higher score for the model B. There are different approaches, of course, to manage ties in interleaving algorithms, and the way you build your interleaved list will, of course, take items that could be in common between the two rankings and assign to the item in the final interleaved list one model or the other, depending on the interleaving algorithm. So what are the advantages that interleaving brings to the table? So it reduces the problem of users variance. So when you have like two different groups, you may have like effectively different kind of users split. So you may have like a problem due to the separation of the users. The interleaving won't separate users. So you don't have this problem here. So all users will be in the same group. And interleaving proved to be, so everything I quoted here, there are many papers that explore in details. So of course, if you are interested offline, I can share some of the links, some of the references, because of course it's not something I state. I mean, many researchers work on that and in the end proved through experiments, hopefully reproducible experiments, that interleaving approaches were more sensitive, for example. So when comparing the difference between two models, interleaving approaches were able to capture smaller differences. Interleaving approaches proved to require less traffic, so less time in the end, because you need less interactions to reach the statistical significance of your results. And another important thing is that if you use interleaving, you in opposition to A/B testing, you don't necessarily show and expose a bad model to your users. So you test it offline, you are actually quite happy of that learning to run model you produce, but online, it could perform very poorly. If you just divide your users into groups, one group will be exposed to a terrible model potentially, and that can be problematic for a business. With interleaving, some of the results within a ranked list may be potentially bad, because of course we are interleaving the ranked list, but we are not messing up entirely the user experience. So that's another factor that is quite positive for interleaving. We are going to give you a quick understanding of two interleaving algorithms. We'll start with balanced interleaving and then spend a little bit more time on Team-Draft Interleaving, and just a glimpse on probabilistic interleaving, which is more complex, and we don't have, it's not really the focus of this talk anyway. So balanced interleaving will, when producing the final search result list as a product of the mix-up of two ranked lists, will alternate the insertion, assuming that one model at the beginning has a higher priority. So we have two models, model A and model B. We decide at the beginning who go first. So for example, could be model A. And then we take the top result from the model A and then the top result from the model B. Then we go back to model A and then go back to model B until we exhausted the results in the two ranked list. Now, the balanced interleaving had some problems, because if an element is already presented to the user in the ranked list, it won't be added again in the final ranked list, and effectively the model will lose its turn. This could end up in some unfairness with the search results. We can give you here an example. So we have the ranked list for the model A, which is returning the documents A, B, C, D. The model B, on the other end, is returning the same group of items in a different order, and it's returning B, C, D, and finally A. So 3 out of 4 of the search results that are in common are with a higher ranking on model B. Just A is the top ranking element in model A and the last ranking element in model B. So with balanced interleaving, at the beginning you decide if model A has the priority or model B has a priority, and that's fixed for your interleaving process. So we could have 2 possible outcomes here, if A is the prior or B is the prior. If A is the prior, we're going to select the document A, which is the top ranking. Then is B turn, and we select the top ranking for B, which is B. Then is A turn, and it would have been B, but we added that already. So is model B turn, so C goes to the ranked list. Then is model A again, C, we've done that already, so model B, D. And then that's the end, because then this is inserted and A was already inserted. So 3 out of the 4 elements on the ranked list are from B. If we select B as a prior, we get a different ranked list, but still B is overwhelming in comparison to A. So when we accumulate user interactions, it's more likely that the user will click on an item that's coming from the model B. So for this reason, balanced interleaving, yeah, okay, performs decently, but can be improved. So the Team-Draft Interleaving tries to solve this problem, applying a Team-Draft method similar to like team captains in team matches, where each captain alternate and select a player, like is hopefully best player among the choices. So with Team-Draft Interleaving, we still select a model that goes first, but at each time we repeat the insertion, we select randomly the model again. So we start with a selection between model A and model B. We add an element from model A and an element from model B. So the difference here is that you're never going to skip a model. So if the element from model B was inserted already, you're going to scan the ranked list and select the following item. So we select one from A, one from B. For example, if we selected A as the prior for the first insertion, and then we randomly select the best model again. So could be again A, or could this time be B. So we add another item for the model that has been selected to go first, and then an item from the model that is selected to go second. We repeat the selection, and on and on and on. So in this way, we obtain a ranked list that is fairer, and the algorithm is quite simple. It's not that complex to be implemented. So most of the times we get a lot of benefits in comparison from balanced interleaving to a little cost, because it's not that much expensive in terms of computational time nor implementation. Of course, there are situations when a Team-Draft interleaving won't behave in an exceptional way. So researchers tended to work on that and improve it and compare it with additional new algorithms. It's still a solid algorithm, Team-Draft interleaving, but has been improved by some other options, especially probabilistic interleaving. You will find on the slides, it's not important to go now in details on this specific scenario, but you will find a potential scenario where Team-Draft interleaving will fall short with its approach in interleaving results. So probabilistic interleaving is the most famous from like the best performing interleaving algorithms, but it's much more complex. So when it's up like to a developer to implement it from the paper, for example, it's a little bit more complicated. So you get some benefits. There are experiments proving that probabilistic interleaving performs better, but probably the gain is not worth the development. Of course, if you have plenty of time, you can experiment with probabilistic interleaving. We are not going to talk about it in details. There are drawbacks for probabilistic interleaving as well, because it's based on probability. So sometimes you could get a less relevant document that is put higher because of an unlucky draw from a probabilistic distribution. So let's take a look to the Apache Solr implementation. So the minimum requirements to run the Apache Solr learning to rank component and the interleaving functionality on top of the learning to rank component are the import of the library of the learning to rank library in your Solr dependencies, in the Solr config XML, the definition of the query parser, which is the LTR Q parser plugin, which is the learning to rank query parser, and the definition of the feature values cache in your Solr config. So this is pretty standard with any learning to rank Apache Solr instance. And if you want to add the interleaving transformer, you will need to declare it in your Solr config. So we're going to see two aspects in the learning to rank interleaving component. One is building the interleaving search result list and takes in input two models. It's actually quite simple to use. And then the transformer is important to show to the final user in the search response to which model each search result belongs to. So learning to rank models currently available in Apache Solr are mostly linear, based on forests of regression / decisional trees, and models based on neural networks. Then you can combine them, you can wrap some of them, you can create like bigger models, and on and on and on. But the main distinction in the current available model is this. And those models are the ones you can use with the interleaving. So effectively, interleaving can be used with any ranking model you can use in Apache Solr learning to rank, and also with the original Solr score. That has been like an important addition at the time of the contribution. So just to give you a very quick refresh on the different models we have in Apache Solr learning to rank, we have a linear model that is just a linear combination of features. The multiple additive trees model, which is the representation of an array of trees in which each tree branches on a feature value and goes to a separate branch and finally calculate the score for the document. And finally, neural network-based models that effectively model the matrix, the different layers of a neural network through their matrices and activation function to be able to calculate the score of a query document pair. You can use learning to rank in Solr using the Reranking query parser and specifying LTR as the query parser, and it takes in input the name of the model you train and deploy to Solr and the quantity of documents you want to re-rank. So out of your results, you want to re-rank the top K results. The learning to rank components also allow you to extract and show to the user the features. And to the user, I mean in the Solr search response, then of course, It's up to you if you want to show it to the final user interface. Normally you don't do that, but potentially you can do that because it's in the JSON results. Finally, you can re-rank your results passing some external feature information, so query time features that can enrich the feature vector with elements that are not present in the index. So when you run a learning to rank query, you will get the results as in a normal search on Solr, and you will have the score and potentially the feature extracted. In this example, I have a book corpus. So each document in the corpus is a simple book with some metadata, such as the title, the number of downloads. This is from the Gutenberg project, and the subjects of the book. Then in this model, in specifically, as you can see in here, the linear model 1 is just one linear model. I uploaded quite a simple model, actually, that combine some of the features. And for example, to give you an idea of how it could look like, is the combination of the scores, which is 1 multiplied by the title length plus 0.5 multiplied the original score plus 10 multiplied with the downloads plus 100 multiplied with the Boolean features, which is its favorite subject, which takes in input the user preference, and then on and on and on. So like 0.5 for times the user age and is user from mobile multiplied by 2. Now, can be really helpful to debug these results. So Solr allows you to, through the features transformer, to show the features with their value. Now, using interleaving with the Apache Solr Learning to Rank module is quite simple. So you just add more than one model. So you pass one model normally, you pass 2 models, and interleaving automatically kicks in. So super simple to use. And you don't need to do much more if you want to effectively just retrieve a mixed result list. So maybe you just want to mix 2 models. You don't want to know if a search result is coming from one model or another. But if you want to then evaluate online your user behavior to try to understand who's the winner, you want to know where they click. And to know where they click, you need to add the interleaving transformer. So the interleaving transformer, so transformers in Apache Solr are components that manipulate the search results, adding some information. In this case, the information that is added is the model that that search result is coming from. So this is the kind of results you're going to get when you run an interleaving query on 2 models in Solr with the interleaving transformer in place. So you will get your documents with all the fields you expressed, plus the interleaving meta fields, which will describe the model the item was coming from. So we can see this with a live experiment, and in the same data set, we can run an interleaving query that is subjects, England fiction, or mystery fiction. So this is going to match a subset of the books in our corpus. We're going to retrieve some of the fields, ID, title, subjects, downloads, score, the features, so the feature vector for learning to rank, and the interleaving model. So we want to know, we mix the results from linear model 1 with the results from linear model 2. We re-rank the top 100 documents, and then we want to know in the interleaving list if the item is coming from the model 1 or the model 2. So this is a live call to a real Solr, and we calculated, so randomly, this can change, of course, because it's randomly assigned. So yeah, I refreshed, and now the first element is the same object, but it's this time coming from the ranking from the linear model 2. If the 2 models offer very different results, of course, we would have seen much different like rankings. In this case, most of them will probably agree. So we won't see particular difference aside from the model that is returning the document, which is every time randomly selected when building the interleaving list. So you can see in here that you have the model the document is coming from. So you can keep these elements in your front end, hidden to the user. You don't need to show it, but when the user interacts with your search results, you are going to be able to know if that click is belonging to the linear model 2, for example, or the linear model 1. On top of that, the interleaving component is compatible with the features transformer. So you're going to see here the features belonging to this model. So they can be slightly different from the feature in another model, and the score, of course, can be different because the two models are two different ranking models. They score documents differently. So for example, in this case, the interleaved list for the models is linear model 2, 1, 2, 2, and 1, 1, 2, and on. And potentially this will change if we refresh. So if we refresh multiple times, now you linear model 2 and 1, 2 and 1, 2 and 1, for example. So the interleaved list changed. It's always going to be one and another, but the order can change and will change after each couple, potentially. And the score, of course, is going to change. So if the first document picked from linear model 2 has a score of 3 million and something, and we refresh as soon as it's coming from model 1, for example, as like a different magnitude of score, because it can be whatever it's. So with interleaving, is not guaranteed that the score is still descending, because of course the elements are coming from different models, from two models. So we could have, yeah, this is a good example. So if linear model 2 is going to build like much higher scores, you're going to have like an inconsistent descending score, right? Because this is coming from model 1, this is with a certain magnitude, and it has a different magnitude, but anyway, is a wanted behavior because you are mixing up results from different models, and you're doing that to then compare how your users interact and clicks and downloads and do with with which of the two models. Now, it's of course very interesting to use interleaving with learning to rank models, but it's equally interesting to compare an interleaving model potentially with your original Solr score. So you may have like just a lexical ranking with the default BM25, a Nedis max query parser returning you a certain result list, and you want to compare that original ranking with a learning to rank model. So to do that is actually quite simple as well. So there's a special keyword in the interleaving component, which is the underscore original ranking underscore. So you may have seen across Solr many times the underscore and the prefix underscore and the suffix underscore for like special kind of keywords, and this is behaving the same. So this is like a special name. So if you want to run your interleaving between a learning to rank model and just your original ranking coming from your original query, you can do that. So you just specify this special keyword, and then you will have in the results the original ranking results mixed up with the learning to rank ones. And the score will be the original Solr score here. So you won't see the features, right? Because this ranking doesn't use any learning to rank features. It's just using the original query, in this case, a Boolean query. So also in this case, quite simple, learning to rank classic approach in the re-ranking. You pass the model you normally pass for learning to rank, and you can interleave it with the original ranking model. So just pass model, equal underscore original ranking underscore. And then, of course, if you're interested, and normally you are, to see where each element is coming from, you can specify the interleaving transformer. So we've done the demo, and just one final remark. I think we should be perfectly in time to leave some time for the questions. So some final remarks for future works and how you could contribute, for example, a new interleaving algorithm. So currently, I haven't actually showed the interleaving algorithm parameter, because currently only the Team-Draft Interleaving algorithm is supported. So you don't need to specify interleaving algorithm equal Team-Draft as a request parameter. This is the default one and the only one. But this parameter is there. So if you are going to implement like a new implementation, so you just need to implement the interface interleaving, which is in the interleaving learning to rank package. You add your new algorithm in the package interleaving algorithms, and then you need, of course, to add it to add the implementation of how you mix up the results and the Solr documentation for that. So it's actually quite easy to contribute. So far, yeah, we just have one, but it's actually quite easy to contribute more. And then you can just use it in here. You pass the name as a different parameter. So one final warning on the limitation. So currently, unfortunately, sharding is not supported because it makes the interleaving problem much more complex, because sharding already is effectively combining results from different shards. Of course, it doesn't combine them in any weird way, just descending on score. But given the fact that the interleaving happens locally, you would have interleaved applied in each shard, and then the elements again like shuffle based on the descending score. So you are going to ruin basically the interleaved list. So currently this is the only limitation, and of course it's open for contribution. So if you feel like you have a solution for that, it's been a while, to be honest. We have not worked, we as committers, on this problem. So there may be, of course, a solution out there, but yeah, we didn't have time to implement it, to work on that. But of course, you are encouraged to do that, and super happy to review any contribution in that regard. And I would like to thank you for your attendance today, and over to Charlie for the final remarks and questions, of course.
Thank you, Alessandro. Fantastic talk as ever. So now's your chance to ask Alessandro questions. If you'd like to type them into the Zoom chat, I'll then ask them on your behalf. We're currently waiting for our first question, so nip in there and you get to ask everything you'd like about learning to rank and interleaving. I can hear the gears turning. I can hear people thinking of questions, even from here. Fantastic. Artem, you're in there first. What tools do you use to train your models?
Okay, so this is more related with the learning to rank side of the component, because of course interleaving takes in input existing models. And currently we mostly use XGBoost, to be honest. In the past I've used Ranklib, which is both of them are open source libraries. XGBoost is Python based, and Ranklib is Java based, mostly command line interface kind of tool, Ranklib, while XGBoost is effectively a library you can use in your Python application quite easily. So yeah, of course, you can use interleaving with whatever tool you use to train your models. It doesn't really matter once you have a model trained. But yeah, this is my recommendation. So nowadays I would say XGBoost is the the tool that we normally use, me and my team, most comfortably.
Okay, thank you. Do we have any other questions for Alessandro? Sunny asked about offline testing your model.
Okay, so for offline testing, first of all, depending on the tool you use for training, those tools normally offers you the possibility of separating your training data between train and test set, potentially development set as well, and they do the evaluation for you offline. So they will give you a result for your learning to rank model, calculated with the same metrics you use to train your model. So assuming you use NDCG, for example, you will see how your model is performing NDCG-wise on your test set. So you just need to, is one of the parameters you pass at training time. You pass the training data and the test data. That's normally what you do. Of course, you can also then potentially deploy the model to Solr and then use, potentially if you want, like Qubit or ReranK Evaluator to do some additional testing. Normally with learning to rank is not something we do because, as I said, as soon as you train it, you also get the offline calculation from the training library you use, but it's absolutely doable for you to deploy the model and then use, as I said, like Qubit from open source connections or ReranK Evaluator from SIS to evaluate your search engine offline.
Fantastic. So Artem has another question. How do you compute features online for the test results?
So if you mean the learning to rank features you use for the model, as I show you, the Apache Solr transformer will add them to the search results. So it's Solr calculates the features to then apply the machine learn model, and you can also view those features. And those features are calculated online. So effectively, when I show you like, yeah, this example, this is a live Solr instance I have now in place. The features are like the title length, for example, the number of tokens for the title, the number of downloads, and those features are calculated online. So they are real features calculated over the document. So these are real values. So on this document.
Thank you.
Did I get your question?
Artem, was that a good answer for your question there?
Yes, I think yes. So basically, your model is applied during the search results for every result, but you trained your model based on this XGBoost, right? And this, so the same XGBoost is used for calculating these features or internal Solr algorithm?
Yeah. Internal Solr. So you need, of course, to match the features definition you use at training time with the feature definition in Solr. So Solr is able to extract your features online at query time, but you need to define, so in Solr you define your features with a feature JSON where you, for example, I think I have an example here where you say the feature called title length, for example, is calculated by Solr using the class Solr learning to rank feature field length feature and takes as a param the field title. So this is the way in Solr you define the feature title length, for example. Then at query time, Solr is able to take each document, calculate that feature, and then apply the learning to rank model. So you need to keep them consistent. So the features you use at training time must be the same features you use at query time.
And are these features already available in Solr, or should I develop my own features?
It depends of the features you need. There are like 4 types of features available. And if in case you have like some custom necessity, you may end up having to implement them. But like document level features that takes in input a field, for example, are there. There is like a way to extract the field length. There is a way to run a query to calculate a feature value. So there are a lot of them available. But of course, in case it's a custom feature that doesn't align with what's available at the time, you may need to implement something.
Yeah, thank you very much.
You're welcome. Thank you. So, Charlie, I think we have Dangshu first. How would you create?
I failed to unmute myself. Yes, Dangshu's question: how would you create the training, test, and validation data split for the LTR model?
So there are various ways for creating the split, and you may also apply your own creativity for doing that. Normally what you do, I mean, you could go randomly with like cross-validation approaches. So you may like divide your sample data in groups, in 5 different groups, and then you make different combination of them. Like you take 3 of them for training, 1 of them for test, 1 for validation, and then you switch each other. So you have different combinations, and then you train the model, and you check which model is the best. You could just go based on the time you collected your data, your sample data. So you would go like, I don't know, the first couple of months are your training, then the 2 weeks after is your test, and or is your validation, and then the latest 2 weeks are test. There are many ways. You can even take a look to like the state of the art approaches. My colleagues Anna and Ilaria have been spending quite a long time recently working on different kind of ways of splitting them. Probably we'll write some blog in the future. So there's no one rule, to be honest. And I would suggest to experiment a little bit.
Okay, thank you. Another question from Sunny. For models that are not built in Solr, how do you plug it in? Thank you. So like CatBoost, for example.
Yeah, so yeah, I forgot to mention the fact that actually XGBoost is not directly integrated with Solr. So XGBoost will return you a model that can be represented in XML, JSON, whatever, but is not directly compatible with Solr. So you will have any way to transform that JSON to the JSON format Solr is expecting. So CatBoost, of course, so I don't know if CatBoost anyway is going to be like lambda mart models, so like regression trees models. I suspect now, it's been a while, I'm not investigating like different training platforms. I suspect it's going to be similar to like XGBoost. So it will output you a model with a specific format. If this model is one of the models supported by Solr, so neural networks, regression trees, or linear model, what you need to do, you will need to apply a JSON transformer. I mean, literally you need to write, I don't know, a Python script or a JavaScript, something, Java script, not a JavaScript, to transform the output of CatBoost to the accepted JSON format by Solr.
Fantastic.
If that helps you, Sunny. Okay.
I think it does, yes. So we've got, Hernan's got a question. I'll try and understand this. What kind of strategies do you recommend to improve effectiveness when there are results not retrieved by the index, but according to the ranking model, this is suggested to be a relevant result?
So, I mean, if it's, so you mean matching problems, I guess. So recall related problems, because of course it must be in the index for the ranking model to assign the score. So that's a completely different problem, right? So learning to rank effectively work on the ranking phase, not on the matching phase. So first of all, Hernan, are you referring to recall-oriented information retrieval task and matching? Yes, okay. And for matching, yeah, that's a completely different story. So there are many ways you can improve your matching capabilities, starting from simple approaches such as synonyms, for example, synonyms expansions that is supported by Solr, synonym, hypernym, and hyponym, actually, potentially not only synonyms. And then in general, what you do to improve or solve the vocabulary mismatch problem is potentially applying document expansions that match the user queries. So you actually you could enrich your documents at index time with additional terms. And in this way, you're going to retrieve those documents for the same query terms. Or you could apply effectively what is called nowadays as neural search approaches. So you may transform your query and your documents to vectors forms and then run vector-based queries. So in that way, many vectorization approaches will try to catch the semantic of your query and of your document potentially, and will solve the vocabulary mismatch problem. So the vocabulary mismatch problem means that you run a query term, that query term is not in the document, still the document is relevant for that query term and you want it to be retrieved. So applying neural search, you need to transform your documents and your queries in vectors and then run vector-based search, which is going anyway to be supported on Apache Solr from Solr 9.0, which is anyway soon to be released, and is another contribution of ours, actually.
Okay. I think, yeah, to come back to the original question, I think the short answer is you do your first retrieval step, you get back, say, 1,000 results, and then you use learning to rank to re-rank those 1,000 results. So if the result you're looking for isn't in that first pass, there's not much learning to rank can do. Okay.
Excellent.
So do we have any other questions for Alessandro? Okay. I think we can let you go. So thank you very much, Alessandro, especially for answering those questions and for a fantastic talk, and your contributions, of course, to the world of Solr are hugely appreciated. And hopefully I'll see you all in person soon. That would be great as well. So just a few final remarks. This talk, of course, will be recorded. Thanks so much to Alessandro for giving it. We do need some other speakers, so do let us know if you could give a talk. We'll have it up on the YouTube channel very soon, and I'll post in the meetup group when it's available. And Alessandro, if you have slides you can send me, I can drop a link there as well. That would be fantastic. So a few other things to mention. The next meetup is coming on the 14th of April, and we have Sudhir Joseph talking about a Elasticsearch, an AI-powered enterprise search platform he's been working on for Cisco, which sounds fascinating. The invite for that will go out in the next day or so. At the end of April, we have, of course, Haystack US in Charlottesville, Virginia. Do take a look. Schedule will be published very soon, and tickets are now available at the Haystack website. We'd love to see you there in person if you can make it. The day before Haystack, there's going to be the first visit to the US of MICES, the mixed camp of e-commerce search. This is a free event, partly with some talks and partly a kind of on-conference model where it's put together on the day. Free tickets, you can register at mices.co. There is, of course, our training courses, Think Like a Relevance Engineer for Solr and Elasticsearch coming in May, and we're doing a course on learning to rank later in the year in August, so check out our training there. And of course, you're all already in Relevant Slack. If not, what you've been missing. So do join Relevant Slack. The link's there, and you can join over 2,300 search experts there. So do jump in. Lots of channels and everything to do with search, including learning to rank, of course. And that's about it for today. I'm very pleased to say that our Haystack Live meetup has now reached over 1,000 members. which is a fantastic milestone. We do appreciate you all turning up. So spread the word, bring your colleagues, and send me some fantastic talks for next time. But we'll see you again back at the Haystack meetup on the 14th of April. Thank you again, Alessandro. My name is Charlie Hull. I'm from Open Source Connections. We're the Search and Relevance people, and we'll see you back here again at Haystack Live very soon.
Thank you. Bye-bye.